Okay, so basically what we're going to do today is do a little bit of a review of how to do some polar graphing in our calculators and then do some by hand and kind of get our brains in gear and ready to handle stuff from pre-cal that we probably don't remember. Okay, so I want you to find the section on polar graphs in your notes. And what I want you to do is grab your calculator because you guys are going to be doing some of this side by side. I strongly encourage you to do this with me and to not fast forward the video. Don't just fill this in off of the key. You need to be doing this with me. So turn your graphing calculator on. If you have an 89, it's kind of similar features, but the 84 is what I'm going to be using on here. So you're going to go to your mode and go to, instead of function, go select polar mode on your calculator. Now when you do that and you go to your y equals, you're going to notice that it says r equals. So what I'd like for you to do is you're going to graph the very first function, which says 2 cosine theta. And if you press this button here where you normally press X, it'll automatically default to theta. Now on your window, that's going to become very important. It defaults from 0 to 2 pi. So like this number here is actually 2 pi. And your theta step is really important as well. It defaults to, I think, pi 12ths, and that's okay. But we're going to make our x min and max a little bit, we're going to make them a little bit squarer. So if you go to your graphing screen now, you're going to notice you can't really tell what it is, what it's doing. I actually want you to go to zoom and go to zoom 5, which is zoom square. Now it did make it square, but I want to zoom in just a little bit. So we're going to zoom in. And we can see that this is a circle. So in this very first one here, I can see it's a circle. It starts at the origin, and it extends out to the point 2, 0, and kind of looks like that. That's a really bad sketch, so hopefully yours looks a little bit better. Things to notice, though, it's sitting on the x-axis. So what I'd like for you to do is I want you to press pause on my video, and I want you to go fill in these very first 6 graphs up here. Spoiler alert, they're all going to be circles. So what I want you to kind of be thinking about while you are graphing these is, how do I know where it goes to? Is it going to the right? Is it going to the left? Is it on the x-axis? Is it on the y-axis? So I want you to take a few moments and make sketches. These don't have to be perfect, just sketches of these 6 graphs of the examples that are on my screen right now. Okay? Okay, so if you're joining me back now, one of the things that you should have is all 6 of these graphs on your paper graphed. So some things I'd like to highlight. Did you notice that all of the examples that had cosine ended up being symmetric over the x-axis? And all of the examples that were sine problems ended up being symmetric over the y-axis. The other thing we notice is that the number in the front actually told us how far out to go. So this one ended up at 2 units out, 3 units out. This ended up going in the negative direction on the x-axis. This ended up going 2 units on the y-axis, 3 units on the y-axis, and negative 3 units on the y-axis. So to sum this all up, we notice that these are all circles, and that our cosine were symmetric over x, and our sines were symmetric over y. Well, why is that? Well, think about the unit circle. What represented cosine? Well, cosine is our x value. What was sine? Our y value. And these are polar graphs. It looks like an xy coordinate plane, but you're actually graphing these on a polar plane, which we'll talk a little bit more about later. The other thing I want you to know is that a positive number meant it went on the positive part of the axis, and that a negative number went on the negative axis. Okay? So now we're going to look at another set of 6 graphs, okay? I'll go ahead and hint to you that these are actually broken up into 3 different types, Okay, so you'll notice that every single one of them has something plus something cosine or something plus something sine. So these are three different kinds of graphs. What I'd like for you to do is graph them. Make a quick sketch on your calculator. All right, so if you're joining me back, you should have all 6 of these graphed. Some things that I want to point out to you. All of my cosine graphs ended up being symmetric over the x-axis. Again, all of my sine graphs ended up being symmetric over my y-axis. That is intentional, okay? So hopefully from pre-cal, you remembered that this was called, back up, let me go to my pen, that these were called cardioids. Cardioids, okay? And you can recognize a cardioid anytime these two numbers are the same. In other words, we're going to say A equals B, okay? This next family of functions are called limicons. And this particular ones are with an inner loop. And we can tell that they are limicons anytime this number is smaller than that number. In other words, A is less than B, okay? This third function over here is actually called a limicon also, but this limicon is called a dimpled limicon. Means it doesn't have an inner loop, it just has kind of a flat edge. And this is going to happen anytime this number is bigger than the number in front. So in other words, A is bigger than B. Okay, let me kind of take my calculator and make it a little bit smaller. Okay, so which ones of these went through the origins? Well, the ones that went through the origin were my cardioids, and my limicons with loops. And the ones that did not were my dimpled limicons. Okay? The only ones that have inner loops are when your B value is bigger than your A value. Now I'm talking about B and A, so what I want you to know is all of these three graphs have the form R equals A plus or minus B, and it's either going to be a cosine theta or a sine theta, okay? And we can tell what it is based on the relationship. So when A equals B, it's a cardioid. When A is bigger than B, it's a dimpled limicon. And when A is smaller than B, it is a limicon with a loop. Okay, so let's go to another family of functions. We're going to do some Rose curves, and I actually want to start with these first 4 up here. I'm going to tell you they're going to be pretty difficult for you to sketch, but what I want to warn you with is pay attention to the number of petals and pay attention to the symmetry of these graphs. Okay, so I'd like for you to go to your calculator and graph these first 4. Pay attention to how long the leaves are and how many petals and its symmetry. Okay, so big takeaways, things I want you to notice. Here's a cosine graph, here's a cosine graph. I have symmetry over x, symmetry over x. Here's a sine graph, here's a sine graph. I've got symmetry over y, symmetry over y. Again, very, 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 very important. This first one has 3 petals. The second one has 5 petals. 3 petals and 5 petals. So basically this number right here actually tells me the number of petals. So anytime you have n theta where n is odd, that is the number of petals, okay? The other thing here is that this number in front tells you how far the leaf extends. So you notice this one extended out 2 units. This one extended out 3 units. This one here extends out 2 units. This one extends out 3 units. So that's pretty important. So anytime we have a rose curve, we're going to have the number of petals, if it's odd, and how far out it extends. Now, the thing you're going to have to be careful with is to figure out what direction it extends in. I'll give you an example. You notice that this sine graph right here, this one, it goes where my petal that's actually on the y-axis is down. But this one here, my petal that's on the y-axis is up. And same thing here. I have 3 petals, but the petal that's actually on the x-axis is on the positive side. And here I have 5 petals, and the petal that is actually on the x-axis is on the positive side again. So you're going to have to test some points and test some values, and we'll talk about how to do that in class. Okay? So what I want you to do now is I have 4 more. These all have even numbers of theta. You're going to get them into your calculator and make a quick sketch. Okay, so fair warning on these ones, guys. My stylist did not do a great job of prepping these. I expect your sketches to be just a little bit better. So let's start with the big things to start with. Here's a cosine graph. It is symmetric over x. Yes, I know it's also symmetric over y, but again, that's because this has an even number of petals. Here, cosine graph, symmetric over x. Here is a sine graph symmetric over y, sine graph symmetric over y. But the petals are slightly different. Whenever we have n theta and n is even, we actually have 2n number of petals. Well, what do I mean by that? Here, this one has 2 theta, but it has 4 petals. Here it has 4 theta, and it has 8 petals. 2 theta, and it has 4 petals. And 4 theta, and this one has 8 petals. So odds, you actually have the number of petals. Evens, you're going to double the number of petals. And the number in front tells us how far out it extends. Out to 3, out to 2, out about a radius of 3, out about a radius of 2. So that's kind of nice because we can tell the symmetry and we can tell how many petals it has. Okay? The last couple types of graphs are going to be a little bit difficult for you to graph. Now you'll notice in your calculator, when you go to graph these, it says y equals, and these are not y equals, r equals, and these say r squared. So you're going to have to, in order to solve for r, take the square root. So I'm going to take the square root of 4 cosine 2 theta. Let's get rid of the rest of this mess. And we go to the graph, you can't really tell what it's doing. Your calculator actually really struggles to graph these kinds of graphs. So what's actually going on here, I've got a point here, and I've got a point here, and I have a point at 0, is I have an infinity symbol here, okay? And when you go to graph this other one, so this is a cosine graph. First off, notice this cosine graph is symmetric over x. Watch what's going to happen with this next one. If I take a square root of 4 and change this to sine of 2 theta, it handles this one just a little bit better. This guy is kind of a sideways infinity. That's a terrible drawing. Okay, it's like a sideways infinity symbol. Okay, and these two graphs are called lemniscates. Okay, lemniscates always have r squared, and they always have 2 theta. And what these are is they're actually like half of a rose curve. By the way, don't forget to go up here and label these all as rose curves. Okay, so those are all rose curves. So lemniscates are like half of a rose curve. This last one, let's go to our y equals, and if we actually just type in theta, this is a really cool graph. To graph this one, I'm actually going to make our max like, I don't know, 12 pi, because I'm going to show you if you don't make this max for theta big enough, it's not going to do what it's supposed to do. And let's zoom out a little bit. Awesome. So this thing is called the spiral of Archimedes, and it literally does that. It makes a spiral. This is the spiral of Archimedes. Honestly, you're not going to see a spiral of Archimedes a whole lot, but it is sure enough super cool. All right. So big takeaways. Do you remember how to graph polar graphs? You are not expected to be able to do all these in your calculator. You're going to have to be able to graph some of these by hand, being able to recognize the type of graph and how to make a quick sketch. Your sketches don't have to be perfect, but you are going to have to be able to recognize these. The last thing I want to review with you is kind of how to graph polar points. Now, a polar graph should look like this. Now, I know all these graphs up here look like XY coordinate planes, but you're actually graphing them on something that looks like this, okay? This is what polar graph paper looks like. So let's graph the point 4, 2 pi thirds. This is r theta, radius theta. So we're going to go to a theta of 2 pi thirds, and we're going to count 4 radiuses out. 1, 2, 3, 4. And this is where point A is located, okay? If I wanted to graph the point 3 and 7 pi 6, I'm going to locate 7 pi 6, and I'm going to count out a radius of 1, 2, 3. And this is where point B would be located. Tricky one is this 5 pi fourths and negative 2. By the way, 5 pi fourths is not actually labeled on here, but it's right there. But what does a negative radius mean? A negative radius means we're actually going to go in this direction, 2, so 1, 2, and we're actually on the side of positive pi fourths, and that's where point C is going to be located. And then for point D, let's do that one in black. I'm going to go to negative pi 6. Remember, negative is in this direction, so that's the same thing right there. And we're going to go out to a radius of 1, 2, and here is point D, okay? The last thing that I want to do with you is remind you of some things from pre-cal that we're going to use when I get you actually in class. So here is y, here is r, here is x. And I want to remind you that cosine, if we have an angle, theta, the cosine is in fact x over r, adjacent over hypotenuse. Sine is opposite over hypotenuse. Tangent is opposite over adjacent. So now taking this information, if I solve this for x, I know that x is equal to r cosine theta. And y is equal to r sine theta. And I can take this x squared plus y squared and say that's equal to r squared by the Pythagorean theorem. So r is the square root of x squared plus y squared. Okay, so I'm going to stop us there because I need for you to be able to come in next class and be ready to go with all of this polar stuff. And we need to be able to convert some polar and rectangular coordinates and be able to graph some stuff. So make sure if you have any questions, you're ready to go with those in class.